Now we proceed into another type of testing method, that is impact test. The fracture behavior of a material, it is different when it is tested at different strain rates. Strain rate is the rate at which a material is strained, it is deformed. So depending upon the strain rate, the fracture behavior, it may be brittle or it may be ductile. So for the case of a material, when tested in tension test at low strain rates, that is between 10 power minus 5 to 10 power minus 1 per second, in the case of conventional tension testing, the material fails in a ductile manner. That means it undergoes some amount of plastic deformation before fracture. It undergoes a shape change, it undergoes thinning or reduced cross section, and finally it undergoes fracture. If the same material, it is tested under high strain rates, as that in the case of impact, which we are going to discuss now, it is loaded at high strain rates, a material, it fractures in a brittle manner. Brittle fracture means it occurs without any warning. It does not give any warning of failure. It fails suddenly. It undergoes fracture suddenly. Whereas in the case of ductile, it undergoes some deformation, shape change, which is an indication that the material is going to fail. So brittle fracture is very dangerous and it is to be avoided in most of the cases. Why? Because it does not give any warning before failure. Consider a small example. Consider a polyethylene material, a plastic material, polyethylene, and stretch this polyethylene very slowly. So before fracture, this material will undergo some amount of deformation because there is enough time for the molecules to disentangle, and then finally the material fractures. When that same polyethylene material, it is subjected to sudden load, it fractures before undergoing any amount of deformation because there is no enough time for the molecules to disentangle. So this is one of the example for the case of high strain rate and low strain rate, where the material shows a different type of fracture behavior. So apart from this strain rate, which contributes to brittle fracture, there are other two factors which also contribute to brittle fracture. The other factors are the temperature. The first is strain rate that we have discussed now. High strain rates is one of the factors which contributes to brittle fracture. Second is low temperature. Higher the temperature, more is the ability of the material to deform plastically. The strength of the material decreases with increase in temperature and ductility increases. Whereas at low temperature, the strength is higher and ductility is lower. So temperature is one of the factor, low temperature is one of the factor that contributes to brittle fracture. Next, the third factor is, we have discussed something about these notches in the case of tension test. This notches which acts as stress raisers that concentrates the stress, and at the vicinity of the notch tracks the state of stress exists, which lowers the shear stress. So the material undergoes fracture rather than plastic deformation. So these are the factors which contribute to brittle fracture. All these factors need not be present at the same time to cause brittle fracture. Any one of these factors or two of these factors may cause brittle fracture. It need not be necessarily that all these three at a time must be present for brittle fracture. Any one of these factors may lead to brittle fracture of that material. Now, in order to ascertain the fracture behavior of that material, the tests that are conducted is, one of the tests is impact test. So this impact test, it is conducted at high strain rates. The strain rates are about 10 to the power of 2 to 4 per second, which is of order 5 to 7 orders magnitude greater than that of tension test. And moreover, this impact test, it is conducted for the materials for which there is a notch present in that material, whereas in the case of tension test, the specimen has no geometrical discontinuities. There are no notches present in the specimen, and the specimen is tested for tension. Whereas in the case of impact test, deliberately before testing itself, the fine notch is machined into the specimen and then it is tested. So at that high rate of loading in presence of notch, what is the amount of energy a material absorbs before fracture is determined from the impact test. If the amount of energy absorbed is greater, it means a material, it is more tough. That means more amount of ductility is there. If the amount of energy absorbed before fracture, it is less, it means the material is brittle. The toughness of that material is low. But the toughness that is derived from the stress strain curve in the case of tension is different from the case of impact test. That is called the tensile toughness, and this is the impact toughness. Whereas in the case of fracture mechanics, we study one more toughness that is known as fracture toughness, which indicates the ability of a material to resist a fracture in presence of flaws. And this test is of more useful or more significant when it is conducted over a range of temperatures. Number of specimens of the same material, they are taken, and it is conducted at different temperatures, at high temperatures, at low temperatures, room temperature, and below room temperature, below 0 degrees centigrade. It is conducted at various temperatures, and data that is collected is what is the amount of energy absorbed by this same specimen when it is tested at various temperatures. So by this one can know whether there is any changes in energy absorbed with respect to temperature. That means whether this material is showing some transition with respect to temperature in terms of the fracture behavior, whether there is any transition from ductile fracture at higher temperatures to that of brittle fracture at low temperatures or not. So this is one of the important factor in the case of impact test when it is conducted over a certain temperature ranges. So this is the important information that can be collected from this impact test. The two widely accepted tests for the impact testing is Charpy and isoid specimens. Charpy specimens, the length of the specimen is about 55 mm, and at the center of the specimen a notch is grooved, is machined into the specimen. This notch, it has a V geometry, V shape, with an angle, included angle is about 45 degrees, and it is 2 mm deep, and the root radius is 0.25 mm, the root radius. This is machined exactly at the center of the specimen. Whereas in the case of isoid, the length of the specimen is higher, that is 75 mm long specimen is taken, and similar notch or V notch is machined in the specimen, not at the center, but it is away from the center of the specimen, that is to about 25 mm from one end. At a distance of 25 mm from one end, a V notch of similar dimensions, 2 mm deep, 45 degrees included angle, and the root radius is about 0.25 mm. So this is machined into these specimens. Isoid specimens, they are especially used for the case of non-metallic materials, to test non-metallic materials, and it is widely used in the case of Great Britain. But nowadays this type of geometries, they are very rarely used, isoids. Whereas the case of Charpy, this is most widely used for the case of metallic materials, as well as this is widely used in United States. So when compared to isoid, nowadays the Charpy specimens are more widely used when compared to isoid. Isoid specimens, they can be of either square cross section or circular cross section, and the difference between these two loading are also different. For the case of Charpy, the specimen is loaded behind the notch and the specimen position is that of simply supported beam, and for the case of isoid, it is cantilever and it is loaded in front of the notch. Specimen is loaded in front of the notch. So in order to cause fracture for these specimens, a pendulum is used, a pendulum which is fixed at a certain height, and the specimen is placed. The pendulum is released from that position. So this pendulum moves along the arc, strikes the specimen, and then it swings to a height which is lower than the height of the initial height. So from this, the energy can be calculated. The potential energy is mg into h, where mg into h is the initial height of the pendulum minus h bar, where it is the height to which the pendulum swings after striking the specimen. So one need not calculate this height to which the pendulum swings, the mass of the pendulum and the gravitational force, because this energy can be directly read by means of a dial gauge. So this is how the tests are carried out for the case of impact test, by using two types of specimens, Charpy and isoid. Now we shall see the dimensions and how the specimen is loaded in the case of Charpy and in the case of isoid. This is the case for Charpy specimen, which is having a length of about 55 mm and having a square cross section of 10 into 10 mm. The notch is machined exactly at the center. This notch dimensions are 2 mm deep. This included angle is 45 degrees, and the tip of the notch, root tip, is about 0.25 mm radius. This is the tip of notch. The root radius is 0.25 mm. Apart from this V notches, the other types of notches are also used, but they are not as widely used as V notch. The other notch that are used are U-shaped notch and keyhole. So these are the other geometries of notches that can be used for the case of Charpy and isoid: V notch, U notch and keyhole notch. But when compared to U and keyhole notch, V notch is more widely used because its severity is very, very high. We have seen in the previous modules, in the case of the stress concentration, for the case of an elliptical notch with a major and minor axis, the maximum stress that is developed at the vicinity of the notch is equal to sigma into 1 plus 2a by b. This is b and this is a. So sharper this value b, higher is the value of maximum stress. It is more the stress is concentrated. It acts as a stress riser more. The severity is more when compared to the notches which has blunt root compared to U and keyhole. So V notch is more widely used because of its severity. So this is for the case of Charpy, the dimensions and the dimensions of the notch. So this notch is machined into the specimen with respect to these specifications. and then it is placed as a simply supported beam. It is fixed into the vise, and then the pendulum strikes behind the notch. This is how the pendulum strikes the sample behind the notch, and it swings to a certain height which is lower than the initial height. So from this one can calculate the energy absorbed in fracturing the specimen. If there is no notch present in this specimen, the specimen, instead of fracturing, it undergoes some shape change. It bends, but it does not undergo fracture. So it does not give the value of energy absorbed in fracturing the specimen. So a notch has to be machined into the specimen so that failure occurs at the notch. And what is the amount of energy that is absorbed in fracturing the specimen? It is derived from this experiment. So another notch, another type of specimen, that is isoid specimen, which is not widely used nowadays, is either circular or square cross section, 10 into 10 if it is circular cross section, and the notch is machined at a distance of about 28 mm from one end. The total length of the specimen is 75 mm. This is the total length of the specimen. A notch is machined at 28 mm from one end of the specimen. So the type of loading for this is cantilever type. So this is how the specimen is loaded. So the pendulum strikes the specimen facing the notch, and it is cantilever type, the position of the specimen, whereas this is the type of simply supported beam, and the pendulum strikes the specimen behind the notch. So this is the difference between Charpy and isoid. This is for the case of Charpy, and this is for the case of isoid. So instead of calculation, directly it is read from me by means of a dial gauge what is the amount of energy to cause fracture for this specimen. The velocity of the pendulum is about 3 to 6 meters per second, and equation for the impact energy absorbed is mgh, mass of the pendulum, g is the gravitational force, h is the initial height, and h bar is the height to which the pendulum swings after striking the specimen. So this test is of more useful or more significant when it is conducted over a range of temperature, because a material which fails in a ductile manner at higher temperature, the same material may fail in a brittle manner when the temperature is lowered. So this is called ductile brittle transition temperature, that is DBTT. The transition from ductile to brittle, which occurs over a narrow range of temperature, transition from ductile fracture at high temperatures to that of low temperature where the fracture is transformed into brittle. So this transition from ductile to brittle, it occurs over a narrow range of temperature, and this is known as ductile brittle transition temperature, which some materials, they show this type of behavior with respect to strain rate, with respect to notches, and with respect to temperatures. So this transition temperature from ductile to brittle, as the temperature is lowered, this can be found out by means of this impact test when it is conducted over a range of temperature. When number of samples, number of specimens of the same material it is taken, and each specimen is subjected to this impact test at different temperatures, and amount of energy that is absorbed in fracturing the specimen is determined. So from this we can plot a graph between the energy absorbed. So the units are which are in joules, energy absorbed, to the temperature. So temperature 0, minus 50, plus 50, 100, so on. So this is the plot which shows between energy absorbed in fracturing the specimen with respect to temperature. At high temperatures, the energy absorbed is higher. It means the material absorbs more amount of energy to cause fracture. And at low temperatures, energy absorbed is low in fracturing the specimen. It means the material behaves in a brittle manner. Here, it behaves in a ductile manner. So there are different criteria to determine the transition temperature, where the transition from ductile to brittle or brittle to ductile takes place. So this transition does not take place at a particular temperature, but it takes over a narrow range of temperatures. So this ductile brittle transition temperature, it's not a well-defined criteria. There is no single criteria to explain that at this point ductile brittle transition takes place, because it occurs over a narrow range. There are several different criteria to explain this DBTT, ductile brittle transition temperature. So for the case of this curve, from which it can be observed that higher the temperature, the energy absorbed is higher. It means the material fails in a ductile manner, and lower the temperature, lower is the energy absorbed, so the material fails in a brittle manner. So in order to establish the criteria for determining the ductile brittle transition temperature, the first criteria is to select a point on the curve where the energy absorbed is maximum and constant. That point corresponds to upper shelf energy, and the temperature as is lowered, amount of energy absorbed is lowered, and it reaches to a constant value. So the point of the constant value of low energy absorbed, this point corresponds to lower shelf energy. So this is the upper shelf energy and this is the lower shelf energy, where the amount of energy is constant and low, where the amount of energy is high and constant, that is upper shelf energy. So this point corresponds to fracture transition plastic. It means that above this, the fracture is completely ductile. There is no evidence of brittle fracture. That point is known as fracture transition plastic. And the point corresponding to the lower shelf energy, which is the lowest energy absorbed and constant value, so below which the fracture is completely brittle, there is no evidence of ductile fracture, that is known as NDT. So this point corresponds to the temperature that is known as NDT, nil ductility transition temperature. It means that below this temperature, the fracture is completely brittle. There is no evidence of ductile fracture, and fracture transition plastic is above which the fracture is completely ductile. There is no evidence of brittle fracture. So this is one of the criteria to determine ductile brittle transition temperature. The second criteria is to draw a tangent to the steep drop portion of the curve. A tangent drawn to the steep drop portion of the curve, and the point of maximum energy absorbed and is constant, where these 2 points intersect. So this point, and for the case of lower shelf energy, similarly draw a tangent to the lower steep drop portion of the curve and the point of low energy absorbed and the constant value, where these 2 points intersects. The tangent intersects to this point. So these 2 points, the average of these 2 points gives the ductile brittle transition temperature. the average of this point and the average of this point corresponds to the ductile brittle transition temperature. The average of upper shelf energy and average of upper shelf and lower shelf energy corresponds to ductile brittle transition temperature. So when the impact test, it is conducted over a range of temperatures, amount of energy absorbed in joules, it is plotted with respect to temperature. Energy absorbed in joules with respect to the temperature. So a plot between energy absorbed in joules with respect to temperature is drawn, where there is a variation in amount of energy absorbed. So amount of energy absorbed is higher at higher temperatures. It means the material is ductile. It fractures in a ductile manner. And amount of energy absorbed is lower at lower temperature. The material is brittle. It absorbs less energy to cause fracture. So there are various criteria to define ductile brittle transition temperature. This ductile brittle transition temperature, it is not particular, it does not occur at a single temperature, at a particular temperature. It occurs over a range of temperature. So there is no well-defined criteria to establish a particular value of ductile brittle transition temperature. So several criteria are there to define this ductile brittle transition temperature, the transition from ductile to brittle over a range of temperature. So thereby various criteria are used to define this dBdt. Among this, the first criteria is to find out the temperature at which the fracture is 100% ductile. So that temperature is known as fracture transition plastic. Find out a temperature at which the fracture is 100% ductile. There is no evidence of brittle fracture. So that temperature corresponds to fracture transition plastic, above which, greater than the temperature, it is 100% ductile, and below which there is no amount of brittle fracture. Similarly, for the case of low temperature at which the fracture is 100% brittle, there is no evidence of ductile fracture. So that temperature corresponds to NDT, which means nil ductility temperature. Temperature below which the material fails completely in a brittle manner. There is no evidence of ductile fracture. So that is known as nil ductility temperature. This criteria is very conservative. The second criteria is to draw a tangent to the steep upper portion of the curve, and the point on the curve where it corresponds to maximum amount of energy absorbed and is constant. So where it cuts the tangent, where it intersects the tangent, that point corresponds to upper transition temperature. Similarly, by drawing a tangent to the steep lower portion of the curve and the point of lowest amount of energy absorbed and is constant, where it intersects the tangent, this corresponds to lower transition temperature. So the average of upper and lower transition temperature corresponds to dBdt. This is the second criteria to define ductile brittle transition temperature. Average of upper transition temperature and lower transition temperature. This is the second criteria. The third criteria is to find out the temperature at which the amount of energy absorbed is 20 joules. So that is the third criteria to find out ductile brittle transition temperature. This amount, 20 joules, was chosen for the case of steels, because during the World War II, extensive tests has been carried out on the steel ship plates. So the amount of energy corresponding to this value, that is 20 joules, beyond which the material has failed only in a ductile manner. So this is one of the defined criteria to determine dBdt. This is for the case of steels. The amount of energy absorbed is 20 joules. The temperature at which the amount of energy absorbed is 20 joules. It is another criteria to define ductile brittle transition temperature. This is for the case of steels. Amount of energy absorbed is 20 joules. That temperature corresponds to dB/dt. So one more criteria to determine the ductile brittle transition temperature is based upon the average value of the energy that is absorbed at higher temperatures. The highest value of energy absorbed and the lowest value of energy absorbed. So average value that corresponds to ductile brittle transition temperature. For example, if the highest constant value of energy absorbed is somewhat, we say that it is around 105 joules, and lowest constant value of energy absorbed is 55. So average of this is 105 plus 55, it is 160. Average of this is 80. So the temperature corresponding to this energy absorbed is dB/dt. The average of the energy of highest constant value and lowest constant value, corresponding average value to that temperature is dB/dt. So 80. So amount of energy absorbed corresponding to the highest constant value of energy absorbed and lowest constant value of energy absorbed. So this average value is 80. Temperature corresponding to this value is dB/dt. So this is one more criteria, fourth criteria to determine dB/dt. Average of energy absorbed of upper shelf values and lower shelf value. Upper shelf and lower shelf energies. Average of upper shelf and lower shelf energies. So the temperature at which the average of upper shelf energy and lower shelf energy. So that corresponds to dB/dt. And the last criteria, the fifth criteria, is depending upon the appearance of fracture. Appearance of fracture. Ductile fracture, the appearance of this type of fracture is fibrous and dull. It gives like a silky appearance, but it is very dull. Whereas for the case of brittle fracture, the appearance is granular, cleavage type, and it is very bright. So by looking at the appearance of fracture, one can say that it is either ductile or brittle. If it is not visible clearly, one can look into an electron microscope. The electron microscope to observe the amount, that is whether it is fibrous or it is granular, whether it is ductile or brittle type of fracture, is by means of scanning electron microscope. So by this scanning electron microscope, one can observe the fracture surfaces and can estimate the amount of ductile fracture and the amount of brittle fracture. So this is one more criteria to determine the ductile brittle transition temperature by means of appearance of fracture surface. So from the same figure, by plotting one more curve with respect to the appearance of fracture, that is the percentage of brittle fracture or the percentage of ductile fracture, we can establish one more criteria, that is the last criteria, to determine dB/dt. This is for the case of energy absorbed versus temperature. Now with respect to percentage of brittle fracture, brittle fracture. This is with respect to brittle percentage of brittle fracture. Brittle fracture percentage is very high. It is almost 100% at low temperatures. As temperature increases, the brittle fracture and percentage decreases. So the point, this point corresponds to dBTT, where the percentage of fracture appearance is 50-50, 50% ductile and 50% brittle. So the temperature at which the fracture is 50% ductile and 50% brittle, this is at that temperature we can establish dBTT, that is the temperature for transition temperature from ductile to brittle. So this temperature is known as fracture appearance transition plastic. The temperature corresponding to 50% ductile and 50% brittle is one criteria to find out ductile brittle transition temperature, and that temperature is known as FATP, that is fracture appearance transition plastic. So these are the several criteria to define ductile brittle transition temperature. So from this impact test, one can determine the toughness, impact toughness, amount of energy absorbed in fracturing the specimen, as well as when it is conducted over a range of temperatures, one can determine the transition temperature from ductile to brittle. dBTT can be determined. So there are certain disadvantages when using a conventional impact testing machines. From the conventional impact testing machines, one can determine the total energy absorbed in fracturing the specimen. But these conventional testing machines, when they are replaced by the instrumented Charpy test, which gives a load deflection curve. So from this, one can determine what is the maximum load and what is the behavior of that material during the application of this load. So one can have more information when these conventional impact testers were replaced by the instrumented Charpy test, which uses a free falling dart which falls freely from a specified height onto the specimen, and when the specimen it is forced by means, it is penetrated by means of this free falling dart, we can have this load deflection curve, which gives more information about the behavior of the specimen under the load, maximum load, etc. All this information can be obtained. Now we shall look into the various factors, various variables that affect the impact toughness of the material, as well as the ductile brittle transition temperature. The various factors that affect the ductile brittle transition temperature are: the first one is the chemical composition. In the case of steel, an increase in carbon percentage of 0.1 weight% carbon, it increases ductile brittle transition temperature to an amount of about 14 degrees centigrade. Manganese, when increased in amounts of about 0.1 weight%, it lowers the transition temperature by 5 degrees centigrade. Phosphorus also has an influence in raising the transition temperature. Phosphorus in weight% of 0.01, it increases the transition temperature, ductile brittle transition temperature, by 7 degrees centigrade. Similarly, nitrogen, silicon also increases the transition temperature, whereas nickel is beneficial in lowering the transition temperature. Apart from this, oxygen is also having a large influence in raising the transition temperature. Oxygen of weight% 0.001, when it is raised to about 0.05 weight%, it changes the transition temperature from minus 15 degrees centigrade to about 340 degrees centigrade. So oxygen content, when increased in levels from about 0.001 weight percent to about 0.05 weight percent, it raises the transition temperature from -15 to 340 degrees centigrade. So the effect in raising the transition temperature is very great in case of oxygen. So in the steel making process, so deoxidation practice has a very important role. So with respect to the chemical composition, these are the various elements which raise or lower the transition temperature. In lowering the transition temperature, manganese is very effective, as well as nickel is also beneficial in lowering the transition temperature. Whereas carbon, phosphorus, nickel, silicon and oxygen, all these raise the transition temperature. They raise this ductile brittle transition temperature. Always one needs to choose a material which is having a lower transition temperature, because as said earlier, ductile fracture, it occurs by warning, by changing the shape of the component, by causing excessive thinning. One can know that this material is going to fail. So it gives a clear indication, ductile fracture, that the material is going to fail. Whereas the brittle fracture, it occurs without any warning. It causes sudden failure. So that is more dangerous. So always choose a material which is having a lower transition temperature. The second factor which influences this ductile brittle transition temperature, apart from chemical composition, is the notch, configuration of notch. Second is the notch configuration. Very sharp notches, they raise the brittle transition temperature, as well as these sharp notches. In the presence of these sharp notches, the material fails in a brittle manner, because sharper is the notch, more is the maximum stress, or the stress concentration is more at the vicinity of the notch. So sharper notches are more severe, as well as the presence of notches, surface cracks also raises the transition temperature. Notches, surface cracks, they increase ductile brittle transition temperature. One more factor that influences the ductile brittle transition temperature is the size. Thicker materials, they absorb less energy when compared to thinner materials, because in the thicker materials there may be some defects present in the thicker material, which lowers the energy required to cause fracture. So with respect to the specimen size, that also has an effect in energy absorption to cause fracture, as well as the transition temperature. A thicker specimen will raise dB/dt, as well as the amount of energy absorbed is also lower. One more factor which affects the ductile brittle transition temperature is radiation. So in the case of nuclear reactors, pressure vessels, where they are subjected to irradiation, that also lowers the energy as well as raises the ductile brittle transition temperature. So this is also one of the effect to increase the transition temperature, as well as to lower the energy absorbed in causing fracture of the specimen. Irradiation is one more factor. Another factor is grain size. Finer grain size material, they lower the transition temperature. So fine grain size material, they lower ductile brittle transition temperature. The amount of energy absorbed before fracturing is also higher for the case of fine grain size material, because fine grain size material, they are more tougher when compared to coarse grain size material. So another factor which is one of the important factor is the crystal structure. Crystal structure also plays a very important role in dB/dt. Among the three types of crystal structures, face centered cubic, body centered and HCP, BCC, they show a variation in dB/dt, ductile brittle transition temperature. So when a plot of energy absorbed versus temperature is drawn for these three types of crystal structures: energy absorbed versus temperature. For the case of FCC, energy absorbed is very, very high, and they are not that sensitive to temperature. And HCP, high strength HCP metals, they also show a very less dependence on temperature, whereas BCC metals, they show a variation of energy absorbed with respect to temperature. This is for the case of BCC. High strength FCC metals, the amount of energy absorbed is very less. They fail in a brittle manner. FCC metals, they show a very high amount of energy, whereas BCC, they show a gradual transition from ductile to brittle manner. At higher temperatures, amount of energy absorbed is higher, which fails in a ductile manner, and as temperature decreases, amount of energy decreases, and they fail in a brittle manner. Now we shall see what is the reason for this ductile brittle transition temperature for the case of BCC materials. The flow stress for the case of BCC metals, it is very strongly dependent on temperature when compared to FCC. So with increase in temperature, the flow stress of the material is lowered. Less amount of energy is sufficient for that material to deform. So the strength of the material is lowered at high temperatures and ductility is high. As the temperature is lowered, the flow stress increases and the material fails in a brittle manner. The fracture strength is same. It does not undergo any change with respect to temperature, but the flow stress, it changes with respect to temperature. Above the transition temperature, yield stress is less than the fracture stress. This is above transition temperature. So the material undergoes yielding before fracture. At below transition temperature, the yield stress is greater than the fracture stress. So the material undergoes fracture before yielding takes place, before plastic deformation takes place. Now we shall see what is this type of behavior in the case of BCC metals, which show a gradual transition from ductile to brittle. So in order to understand this mechanism for the case of BCC metals, we first look into the thermally activated process. What are thermally activated process? Thermally activated process means the processes which undergoes changes with respect to temperature. When sufficient amount of thermal energy is provided to a system, some changes occurs with respect to the thermal energy provided. So the process which depends on this thermal energy or with respect to the temperature, they are known as thermally activated process. When a shear stress is applied onto a material in order to deform that material, there are some forces which restrict the plastic deformation. There are certain obstacles present which restrict the plastic deformation, which oppose the forces to cause plastic deformation, which are of two types. One is known as long range obstacles and second is known as short range obstacles. Long range obstacles which resist the plastic deformation. Second is short range obstacles. Long range obstacles means they do not depend upon temperature and strain rate. They are independent with respect to temperature and strain rate. Whereas in the case of short range obstacles, which are dependent upon temperature and strain rate. With increase in temperature, these obstacles can be easily overcome But for the case of long range obstacles, with increase in temperature, the obstacles which cannot be overcome, those are known as long range obstacles. Some of the examples for this long range obstacles, while discussing in the strengthening mechanism, have discussed about the dispersion strengthening, the dispersoids. The dispersoids which do not undergo coarsening even at very high temperatures. So they act as effective obstacles even at higher temperatures. Whereas for the case of precipitates which undergo coarsening, they lose their coherency at higher temperatures, as well as they undergo coarsening, whereby the dislocations can easily bypass them, so that the dislocations can easily surmount these obstacles with respect to temperatures. So dispersoids are one of the example for long range obstacles which cannot be overcome by means of temperature and strain rate. And for the case of short range obstacles, we have dislocations themselves, that is for the case of intersection of dislocations, that is strain hardening, which can be easily overcome at high temperatures, because at higher temperatures dislocation annihilation takes place and the dislocation density comes down. Dislocation themselves, then short range obstacles which depend upon temperature and strain rate are precipitates, Peierls, Navarro stress. This is a stress required to force a dislocation to move through the crystal lattice. Peierls-Navarro stress, you might have studied in the dislocation theory, the force to move a dislocation through the crystal lattice. Peierls-Navarro stress is given by 2g into 1 minus nu e to the power of minus 2 pi a by b, where a is the distance between, it is the distance between the planes, and b is distance between the atoms. When a is less than b, tau p is higher, that is the Peierls-Navarro stress is higher. This is the case for the case of BCC metals which are loosely packed, whereas FCC and HCP, they are closely packed. So A is the distance between the planes when the planes are closely spaced but they are loosely packed. B is the distance between the atoms. So in this case, Peierls-Navarro stress is higher. So this can be overcome by means of thermal energy. At higher temperatures, this barrier can be overcome. So this comes under the short range obstacles. So apart from this, the various other short range obstacles are dislocation, climb, etc. They are the other obstacles which can be easily surmounted by the temperature as well as strain rate. So now probability for a process to which is having an energy to occur at an energy of higher state, delta E minus of kT, is proportional to exponential of minus of delta E by kT. It is probability for a system to attain at a state greater than energy, that is delta E, is given by this equation, which indicates that higher the temperature, easy for the process to be in that state. So with respect to the case for the dislocation during plastic deformation, it is given as exponential of minus of Q is the activation energy for the barrier minus V star. It indicates the activation volume for the dislocation which are taking part in the plastic deformation into tau prime, that is the applied stress, by kT. So this equation states that lowering the energy barrier and increasing the temperature, obstacles can be easily surmounted. So from this, it can be understood that for the case of BCC metals, the flow stress is very strongly dependent upon temperature. Higher is the temperature, lower is the flow stress. With decrease in temperature, the flow stress increases, but the fracture stress remains unchanged with respect to temperature. Next, this flow stress is also strongly dependent upon strain rate. So when considered for two materials, BCC and FCC, and this is BCC when conducted for a particular strain rate epsilon 1, and BCC when conducted for a strain rate epsilon 2, which is greater than epsilon 1. This is for the case of BCC and this is for the case of FCC. From this, which is verified experimentally, it can be seen that flow stress is strongly dependent upon the strain rate.